Hi everybody, and welcome to this week's module on text retrieval and search engines. So far, we have looked at general pre-processing techniques and algorithms that manage mostly structured data. But what about unstructured data in, for example, social media like Twitter or Instagram, or in customer feedback on product or merchant websites like, for example, Amazon.com? That's what this week is about. Well then, let's jump right into the text retrieval and search engines problems. This will lead us into the field of natural language processing, or NLP. When thinking about NLP, here are some of the big questions we will have to address. Why is it so hard for a computer to figure out what I'm saying? Aren't words just words? And can I just put them into a big dictionary for my computer to count? What is a vector space model? And can it help solve these problems? And since there's dot product on this slide, does this mean that cosine similarity is making a comeback? Well, let's see. Here's a small diagram of what we're about to explore. Let's say that the big text data shape at the bottom of the slide is all the web pages on the World Wide Web, not to be confused with the internet, which is far bigger than the World Wide Web. We can then use natural language content analysis in the yellow box here to pre-process our data and either feed them into a recommender system or a search engine, that is, facilitate text access for algorithms that we build. The end product is a small set of relevant data that we present to our end user. Going back to our search engine then, we will have to search through the text, which we have pre-processed with our natural language content analysis, with various methods. In our case, we will specifically look at the vector space model because it is the basis for most search engines today. A dog is chasing a boy on the playground. We typically don't have any problems understanding the sentence. But imagine what the computer would have to do in order to understand it. You're right. It would have to deconstruct the sentence into its grammatical parts, from parts of a sentence down to word types and even their meanings. So it would have to do the following. First, it would have to know dog is a noun, chasing is a verb, etc. So this is called lexical analysis or part of speech tagging. And we need to figure out the syntactic categories of those words too. So that's the first step. After that, we're going to figure out the structure of the sentence. So for example, here it shows that a and dog would go together to form a noun phrase. Is and chasing is a complex verb which makes up a verb phrase together with a and boy, and so on. The larger issue, though, is not just dissecting the sentence into its parts. It is deciphering the context. In other words, determining why this observation that the dog is chasing the boy in the playground is worth mentioning. Is the dog scared? Is the boy scared? Is the observer scared? Or are the dog and the boy just playing? This is what we call an inference. Is the observer talking to the dog's owner and indirectly prompting him or her to call the dog back? In the case in which an act of saying something is really the performance of an action, that's what we call a speech act. So without sophisticated algorithms and dictionaries, a computer really can't make even the simplest decision between all these options, that is, a positive or a negative inference or a speech act. We have to help. Natural language is designed to make human communication efficient. As a result, we omit a whole lot of common sense knowledge which we assume the hearer or reader possesses. Look at the examples in the yellow boxes here. These are just some of the examples in which our common sense and our understanding of context allows us to resolve ambiguities and context problems. Lastly, think of another problem that just reading a sentence brings with it. Can you guess it? If you guessed voice tone and body language, you'd be right. Me saying, "Oh, great," and "Oh, great." That's two different meanings, isn't it? But it's the same words. And the only way you can tell whether I'm seriously excited or bummed is the tone of my voice here. And, if you could see me, my facial expression, the movement of my hands, and perhaps my stance. So how is a computer supposed to decode all of this extraneous information that isn't included in a written sentence? This is why robust and general NLP tends to be shallow, while deep understanding doesn't scale up. With good dictionaries and algorithms, we can tag parts of a sentence reasonably well. But what about semantics, that is, inferring the real meaning of a sentence in its context, especially when that context is missing? Or what about parsing some basic meaning, but determining what the action should be that would follow the sentence? This is where the human brain, with its 5 senses, is still better than any computer. And this is our challenge. But let's start with a few examples. Over the years, we have developed algorithms that can well identify grammatical or word usage issues in your document, or even analyze the tone of your language. That's what we're seeing here in the example from Grammarly.com. Or take a look at the example at the bottom from Google Translate, which happens to be the beginning of a very famous poem by the German poet Johann Wolfgang von Goethe. That looks pretty good, doesn't it? Most of it was understandable, except for the hard semantic part of cleaned people versus well-dressed people. Now, the search engine performs is much simpler than the task a translation engine performs. And here, matching the query words in a search to the content of the web pages or documents found is usually a great start. So, now that we've looked at the problems in language content analysis, let's talk about text access and retrieval mode. When we talk about text retrieval, we have one of two options, pull or push. Assume that you want to buy a new phone and want to read technical product reviews. One of the sites you could use is TechRadar. You type TechRadar into your search box, and from the millions of returned results, you pick the one you think will work best for your purposes. That's pull mode. Once you've read your article, a pop-up offers to send little notifications to your computer that will let you know as soon as a new article is added to the website. If you click Allow, you have just established push notifications, meaning that the website can push a little pop-up about any update to your computer's system tray. For our task, we will concentrate on pull mode because that is still the most popular way in which information is being retrieved. Although automatic data updates for advanced analytics and corporate dashboards are very much in use in enterprise contexts. As we are zooming in on search engines, we will need to clarify some vocabulary and basic math before we step into our analysis and model. Simply said, retrieving text is different than retrieving information or data. When we retrieve data, we often do that from structure-based systems such as relational databases or non-relational data management systems. No matter which of these we're talking about, we have to use well-defined semantics to get the answer we're looking for. For that purpose, we use specific languages such as SQL, JSON, GraphML, and so forth. And if our syntax is just right, we get specific matched records and are on our merry way. Much in contrast to text retrieval. How about you pull up any search engine in your web browser and type in cat, as I've done here? And we all know that the internet was made because of cats, right? As you can see in my example, I did just that. Apart from really awesome cat videos here, the first entry was in fact all about the animal, which is what I had intended. The second entry, however, was about the construction equipment manufacturer Caterpillar, which also uses CAT as its abbreviated company name. So perhaps cat was not the best search term, not only because it led to ambiguity, but also because it retrieved documents that weren't specific to my intended search. In text retrieval, getting search terms right with the precision of a programming language is really critical to producing the greatest number of relevant documents. But let's first get some vocabulary out of the way. Speaking of which, vocabulary V means all the words. That's W1, W2, all the way to WN in one or more languages. A query Q contains search terms Q1 through Qn, and the search terms are part of the vocabulary. A document D contains document words D1 through DM, and the words are part of the vocabulary. A collection C contains all the documents retrieved following the execution of a query. Now we are ready to determine which documents in the collection are really relevant to the query and which ones are not. Remember my previous example with the animal cat and the company caterpillar? Our goal then is to be able to compute an approximate relevance index or factor that helps us determine which documents are more relevant than others for our query. For that purpose, we could, for example, investigate each document that our query returned and apply a simple binary classifier. If the document is relevant, it gets a 1. If it isn't, it gets a 0. That would be a very basic document ranking system. For that, we could apply two strategies. Our first strategy is a document selection strategy. Here, we indeed calculate the relevance for a document in our collection if the document and the query either match, that's a 1, or don't match, that's a 0. So we can write and use a simple binary classifier that sorts based on absolute relevance. Our second strategy is a little more complex. We can calculate relevance for a document in our collection based on whether the document and the query match to a specific extent. That is a threshold or a cutoff that we specify. If a document passes this threshold relative to the query, it would become part of a relevant subset or class. That looks more like a probability or regression problem, doesn't it? We would have to compute the likelihood with which one document is more relevant than the other. What would this look like in practice? Well, let's assume the oval to the left here is our collection. We have identified 5 documents as relevant and the others as not. If we use a basic binary classifier in our document selection, we will identify most of our relevant documents, and because there's always error involved, some of our non-relevant documents, and some of our relevant documents may show up as false negatives in our non-relevant group. If we use document ranking and specify a threshold of, say, 0.8 or 80%, we will find that some not relevant documents will show up above the threshold and some relevant documents may still appear as false negatives. Our goal will be to optimize this classification. The big problem with binary document selection is classifier tuning in order to minimize false positives and false negatives. This is where document ranking will do a much better job, especially if we consider that some documents may be of higher relevance than others that are still also useful, but not, say, in the top 10. So our problem of the day then is how to design a solid document ranking function and how to optimize the selection of our relevance threshold. So thinking about the retrieval methods then brings us to the problem of how to design a ranking. Back to vocabulary. The problem is the following. We have a query that has a sequence of words and the document that's also a sequence of words. And we hope to define a function f that can compute a score based on the query and the document. So the main challenge is with designing a good ranking function that can rank all the relevant documents on top of all the non-relevant ones. Clearly, this means our function must be able to measure the likelihood that a document D is relevant to a query Q. That also means we have to have some way to define relevance. In particular, in order to implement the program to do that, we have to have a computational definition of relevance. And we achieve this goal by designing a retrieval model, which gives us a formalization of relevance. Basically, we assume that if a document is more similar to the query than another document is, then we will say the first document is more relevant than the second one. So in this case, the ranking function is defined as the similarity between the query and the document. One well-known example in this case is the vector space model, which we will cover in more detail later. A second kind of model is the probabilistic models. In this family of models, we follow a very different strategy where we assume that queries and documents are all observations from random variables. And we assume there is a binary random variable called R here to indicate whether a document is relevant to a query. We then define the score of document with respect to a query as a probability that this random variable R is equal to 1, given a particular document query. There are different cases of such a general idea. One is the classic probabilistic model. Another is a language model. Yet another is the divergence from randomness model. A third kind of model is based on probabilistic inference. So here the idea is to associate uncertainty to inference rules, and we can then quantify the probability that we can show that the query follows from the document. Finally, there's also a family of models that are using axiomatic thinking. Here, an idea is to define a set of constraints that we hope a good retrieval function will satisfy. So in this case, the problem is to seek a good ranking function that can satisfy all the desired constraints. Interestingly, although these different models are based on different thinking, in the end, the retrieval function tends to be very similar. And these functions tend to also involve similar variables. These models are all based on the assumption of using bag of words to represent text. So with this assumption, the score of a query, like a presidential campaign news with respect to a document of D here, would be based on scores computed based on each individual word. That means the score would depend on the score of each word, such as presidential, campaign, and news. And here we can see there are three different components, each corresponding to how well the document matches each of the query words. Inside of these functions, we see a number of heuristics used. So for example, one factor that affects the function D here is how many times does the word presidential occur in the document. This is called a term frequency, or TF. We might also denote that as C for count of presidential in the document. In general, if the word occurs more frequently in the document, then the value of this function would be larger. Another factor is how long is the document. And this is to use the document length for scoring. In general, if a term occurs in a long document many times, it's not as significant as if it occurred in the same number of times in a short document. Because in a long document, any term is expected to occur more frequently. Finally, there is this factor called document frequency. That is, we also want to look at how often presidential occurs in the entire collection. And we call this document frequency, or DF, of presidential. And in some other models, we might also use a probability to characterize this information. So all these are trying to characterize the popularity of a term in a collection. In general, matching a rare term in the collection is contributing more to the overall score than matching up a common term. So we assume that if a document is more similar to a query than another document, then the first document will be more relevant than the second one. And this is the basis for ranking documents in this approach. And this brings us to the vector space model. Imagine a three-dimensional space where each dimension corresponds to a term. Here we have a three-dimensional space with three words. We have presidential, campaign, and news. So each term here defines one dimension. Now we can consider vectors in this three-dimensional space. And we're going to assume that all our documents and the query will be placed in this vector space. So for example, one document might be represented by this vector, D1. Now this means this document probably covers news and presidential, but doesn't really talk about campaign. Now this is different from another document which might be recommended as a different vector, D2 here. Now in this case, the document that covers campaign and news doesn't really talk about presidential. So the topic of D2 is likely about some marketing campaign or information campaign updates, and that shows us that by using this vector space reproduction, we can actually cover the differences between topics of documents. Now you can also imagine there are other vectors. For example, D3 is pointing into that direction of campaign and presidential, but not news. In fact, we can place all the documents in this vector space and they will be pointing to all kinds of directions. Similarly, we're going to place our query also in this space as another vector here. And then we're going to measure the similarity between the query vector and every document vector. So in this case, for example, we can easily see that D2 seems to be the closest to this query vector, and therefore D2 will appear higher than the others in our search result hierarchy. All of this sounds great, but the real question for our vector space model is what goes on the axes? That is, what are the basic concepts that we're looking for? And how do we imagine the vector for our query and for our matching documents if the query contains terms that are more and some that are less important, and we measure that term importance with weights? The same goes for documents. Where do we place the vectors for documents if they contain more of the heavyweight terms or more of the lightweight terms from the query? Lastly, how do we define the similarity? Let's say that each word in our vocabulary defines one dimension in our vector space model. That's a lot of dimensions, but it's the only way in which we can locate both our query and our retrieved document space. Here we see a query with words from x1 to xn and a document with words from y1 through yn in this space. We can now use simple on-off or 1-0 bits to compute the similarity between the query and the documents. If a word from the query appears in the document, the value is 1. If it is absent, the value is 0. The shorter the query and the longer the retrieved document, the fewer ones and the more zeros we get. Okay, so now we have our ones, now zeros. Now we can start computing the dot product between the vector for the query, here shown in red, and the one for the retrieved document, here shown in blue. Since the results will be different for different retrieved documents, that can get us some sort of crude document ranking. So to summarize, in our vector space model, each word from our bag of words is a dimension. We measure absence or presence of a word from our query in a retrieved document with an on-off or 1 or 0 bit vector. Then we can calculate the similarity between query and document with the dot product, and we have our first ranking function. Now let's look at an example. The sample query is news about presidential campaign. We have 5 documents which cover different terms in the query. Some documents are probably relevant and some others are probably not relevant. Most of you would agree that D4 and D3 are probably better than others because they really cover the query well. They match news, presidential, and campaign. They should be ranked on top. The other 3, D2, D1, and D5, are really not all that relevant. So we can also say D4 and D3 are relevant documents, and D1, D2, and D5 are non-relevant. Now let's see if our simplest vector space model could do the same, or could do something better. So let's first think about how we actually use this model to score documents D1 and D3, and the query within the available vocabulary. In the vector space model, of course, we want to first compute the vectors for these documents and for the query. Note that we're assuming that we only use 0 and 1 to indicate whether a term is absent or present in the query or in the document. So these are 0, 1-bit vectors. The query has 4 words. So for these 4 words, there will be a 1. And for the rest, there will be zeros. Same with the documents. So D1 has 2 ones, one for news and one for about, and the rest is all zeros. So now we are computing the dot product here, and the dot product gives us a 2. We're also doing the same thing for D3. We're seeing D3 has news and presidential and campaign. So we are again computing the dot product between the query Q and D3, and our result is 3. So we can see here now that D3 has a relevance function output of 3, whereas D1 has a relevance function output of 2. This means that D3 is mathematically more relevant to our query than D1 and should appear higher in our search result hierarchy. However, if we examine this model in detail, we will have some problems. We're seeing that this simple measure here means if a document matches more unique query terms, then the document will be assumed to be more relevant. That does seem to make sense when we're talking about D1 and D3. The only problem here is that we have 3 documents, D2, D4, and D3, that are tied with a 3 as a score. But if you look at them carefully, it seems that D4 should be ranked above D3 because D3 only mentions presidential once. But D4 mentions it multiple times. In the case of D3, presidential could be a dimension, but D4 is clearly above presidential campaign. Another problem is that D2 and D3 also have the same score. But if you look at the 3 words that are matched in the case of D2, it matches news, about, and campaign. In the case of D3, it matches news, presidential, and campaign. Intuitively, this reads better because matching presidential is more important than matching about, even though about and presidential are both in the query. So intuitively, we would like D3 to be ranked better than D2, but this model doesn't do that. It means that our model is still not good enough and we have to solve these problems. So instead of using a bit vector that measures just the presence or the absence of a word with a 1 or a 0, how about instead using the count of the word's presence in the query and in the retrieved document? This will allow us to preserve our dot product ranking function, but the values we use as its basis will change. Let's see how these vectors work for D2, D3, and D4. While the math does not change for D2 and D3 because each word appears only once, or doesn't in the case of D2, which is missing the word presidential, the math does change for D4. Since the word presidential appears twice here, we get a count of 2 as input for our similarity function. This changes the output from 3 to 4. Now we have mathematically shown that D4 is more relevant than D2 and D3. But that still leaves us with D2 and D3 having the same value. We know that one of these documents is more important than the other, right? If we compare D2 and D3, we see that they both contain the words news and campaign. But there are two really important differences between them. D2 contains the word about from our original query. D3 contains the word of, not in our original query. D3 contains the word presidential from our original query, and D2 contains the word organic food, not from our original query. Now we have to make a decision. Which difference is more important? The difference between about and of, or the difference between organic food and presidential? Since about and of can mean pretty much the same thing here, I'm sure you'll agree with me that the difference between organic food and presidential is much more important to consider. So how do we do this mathematically? Well, mathematically we can penalize the unimportant difference between about and of by reducing its value. Even though about is in our query, the value of the word about is really not equal to the value of presidential. So about doesn't get a 1, it gets something less than a 1. In contrast, since the value of the word presidential is very high to us, presidential gets a value that is greater than 1. So if we use our dot product similarity function again to compute our ranking with these inequalities, we see that the output for D3 is greater than 3, and the output for D2 is less than 3. Using these inequalities, then, we have mathematically proven that D3 is a more valuable document than D2 and should be ranked higher. This is, in fact, how vector space models work in an enterprise environment, very often with computed term values. But there's more to this. Let's look at our vector space model graphic again. We're now not just looking at the count of a query word in the document anymore, but at the value of the words themselves. Computing the value of the words themselves happens with the help of a function. This function is called the inverse document frequency function, or IDF. The inverse document frequency function, or IDF, essentially penalizes popular terms such as about, of, is, was, have, has, over, above, and so on. We calculate the inverse document frequency function by dividing the total number of documents by the number of documents with the term k in it, and we take the log of that. Remember how the internet was made for cats? Well, here's a quick example for term frequency inverse document frequency. If we consider a document containing 100 words wherein the word cat appears 3 times, then the term frequency, that is the TF for cat, is then 3 out of 100, which is 0.03. Now assume we have 10 million documents and the word cat appears in 1,000 of these. Then the inverse document frequency, that is the IDF, is calculated as the log of 10 million divided by 1,000, and that is 4. So the TF-IDF weight is the product of these two quantities, 0.03 times 4, which makes the TF-IDF weight 0.12. Now let's go back to our presidential campaign and apply this concept. We have calculated the IDF weights here for news, about, presidential, and campaign, and a whole lot of other words that we have found in our articles. We multiply these weights with the term frequency numbers, that is, the counts of how often the word shows up in the retrieved document. Because the word about gets a calculated weight of 1.0 and the word presidential gets a calculated weight of 2.5, we can now clearly see the difference between D2 and D3. D3 now contains the more valuable word and ranks higher at 7.1 than D2 at 5.6. Now let's consider our vector space model with TF-IDF weights. If we apply the IDF weights to all of our documents, we get the following rankings. D5 ranks the highest because the word campaign shows up a lot, and I don't know if you remember from the last slide, but that word had an IDF weight of 3.1, super high. D4 gets a good ranking because all the terms appear with presidential showing up twice. And D3, D2, and D1 look about right. But hey, what about D5 with a result of 13.9? It doesn't contain presidential at all. We need to fix this. We have just seen that using a pure TF-IDF model may get us into trouble when we have a high frequency, high value word. We need to correct for this. Since we cannot correct for the IDF weight without changing our IDF function, let's see what happens when we correct for word frequency. This is where document length comes into play. We would expect that our valuable word should show up more often in a longer document than it would in a shorter document. So if our valuable word campaign shows up once in a document with only 100 words, that makes the document more important than a document of 5,000 words in which our valuable word campaign shows up only twice. We're looking at a concentration of 1 in 100 for D4 and 2 in 5,000, which simplifies to 1 in 2,500 in D6. In other words, D4 has a higher valuable word concentration than D6. We measure this concentration with what is called a document length normalizer. The key here is to get the penalization coefficient right. So rather than working from an absolute word number in a document or from some sort of threshold, we use the average length of all relevant documents as our guide. If a document is shorter than our average document, an appearance of our valuable word gets more weight. If a document is longer than the average length of all relevant documents, an appearance of our valuable words gets less weight. That's what is called a pivoted length normalizer. The pivot point here is the average length of all. Here's what this looks like mathematically. In the graphic here, the x-axis shows us the document length. The blue triangle points to our pivot point, the average length of all relevant documents. We now calculate B, the slope that compares the concentration of a term in a shorter versus a longer document. Look at the normalizer formula in the upper left-hand corner here. If there is no difference in the concentration of a term in a short versus a long document, then B is equal to 0, and the normalizer is 1. If B is greater than 0, the normalizer increases, which means that the shorter document is rewarded and the longer document penalized. Now, there is more than one way of doing this, depending on how to apply the log and log normal functions. Here you see the formulas of the two most popular functions, the simple pivoted length normalization vector space model and the BM25 function. These are great to know of for our purposes. If you are interested in pursuing this topic further, please feel free to research. So we have seen how our vector space model can help us determine the ranking of retrieved documents relative to our query. And yet, there are a few things we still have to consider. If each word is a dimension rather than reducing their value with our TF-IDF model, shouldn't we perhaps reduce these dimensions by excluding words that are clearly not relevant, such as these little about, of, if, is, have, and so on words? These are also often called stop words, and in fact, a lot of dictionaries exist that contain these stop words and help us remove these from our calculations. That can speed our search result evaluations up considerably. Secondly, the words cat and cats would be considered two dimensions because they are two different words. The same with the words run and running. Should they perhaps be considered as just one? This is where reducing a word to its semantic stem comes in. This technique is considered stemming. And what about emojis in texts? Are we interested in those, or do we want to exclude them? What about URLs? There are functions in our two favorite programming languages, R and Python, that can help us normalize, yes, normalize, all of these terms. There also has been much research on how to optimize the similarity function. So instead of our basic dot product, which we've used so far, we're going to actually measure the angle between a query and a retrieved document, and thus going to employ a concept we've come to know and love earlier in this course, cosine similarity. So to summarize, in our vector space model, we compute the relevance of a document relative to a query by the measurement of their similarity. We represent both document and query as vectors in an area in which each word from our bag of words represents one dimension. We then design our ranking functions heuristically using term frequency weighting and transformation and inverse document frequency weighting, along with normalization based on the document length. For this purpose, the pivoted normalization and the BM25 algorithms have been very popular. And in order to reduce the enormous amount of dimensions, we can use stop-word dictionaries and other techniques such as stemming, uppercase, lowercase transformation, and more. And now, on to some happy coding.